Welcome to this problem walkthrough. In today's session, we'll dive into LeetCode problem number 1227, titled Airplane Seat Assignment Probability. This problem challenges us to calculate the probability of the last passenger sitting in their assigned seat, based on a unique set of constraints. We'll explore the logic, break down the solution step by step, and understand the underlying concepts. Let's get started. In this problem, we're dealing with n passengers boarding an airplane with exactly n seats. The passengers board in the order of their ticket numbers, starting with passenger number 1 up to passenger #n. However, there's a twist: the first passenger loses their ticket and chooses a seat randomly to sit in. After that, every other passenger follows a simple rule. If their assigned seat is available, they sit in it. Otherwise, they randomly choose one of the remaining available seats. Our goal is to calculate the probability that the last passenger #n, will end up sitting in their own assigned seat. The input to the problem is an integer n, representing the number of passengers and seats, and the output is a floating point number that gives the probability, formatted to 5 decimal places. Let's explore some examples to clarify the problem further. Let's look at the first example. When n is 1, there's only one passenger and one seat. Since passenger number 1 is the only one boarding, they will sit in the only seat available, which happens to be their assigned seat. So, the probability that the last passenger, in this case passenger number 1, sits in their assigned seat is 1.00000. In the second example, when n is 2, things get more interesting. Passenger number 1 randomly chooses one of the two seats. If they happen to choose seat 1, passenger number 2 will sit in their assigned seat, seat 2. On the other hand, if passenger number 1 chooses seat 2, then passenger number 2 cannot sit in their assigned seat. Since passenger number 1's choice is completely random, there's a 50% chance for each scenario, so the probability that passenger number 2 sits in their assigned seat is 0.50000. Now, consider the case where n is 3. Passenger number 1 still randomly chooses one of the 3 seats. Depending on their choice, the outcome for the other passengers changes, but ultimately, the probability that passenger number 3 ends up in their assigned seat remains 0.5. This is because, as we analyze the different possibilities, a pattern emerges. Regardless of how many passengers there are, beyond n equals 1, the last passenger's probability of sitting in their assigned seat stabilizes at 0.5. This symmetry in the random seat selection process holds true even though the process may appear more complex with more passengers. Finally, let's review the constraints and a key insight about the problem. The number of passengers, n, can range from 1 to 100,000, and the output must be a floating point number rounded to 5 decimal places. The solution to this problem lies in recognizing that when n is greater than 1, the probability of the last passenger sitting in their assigned seat doesn't depend on the value of n. It remains constant at 0.5. This is due to the symmetrical nature of how seats are chosen randomly. The only exception is when n equals 1, where the result is trivially 1.00000, since there's only one seat available. This symmetry simplifies the problem significantly, making it computationally efficient to solve even for large values of n. To solve the problem of calculating the probability that the last passenger ends up in their assigned seat, we can consider multiple approaches. One option is the brute force method, where we simulate the seating process for every possible order in which passengers might choose seats. The idea is straightforward: count how often the last passenger ends up in their correct seat and divide that by the total number of permutations. However, this method comes with a significant drawback: it requires generating all possible seat arrangements for n passengers, which has a factorial time complexity of O(n). This quickly becomes computationally infeasible as n grows, making brute force an impractical solution for larger input sizes. While this method provides a direct way to compute the result, its inefficiency limits its usefulness in this problem. An alternative is the recursive or dynamic programming approach, which leverages the problem's recursive structure. If passenger 1 picks their assigned seat, the probability of success for the last passenger remains unchanged. If passenger 1 picks another seat, the problem reduces to one involving fewer passengers. This recursive relationship allows us to define the probability P(n) for n passengers. Specifically, P1 is 1, since a single passenger always picks their own seat. For n greater than 1, p, n, can be expressed as 1/n plus n2/n asterisk p, n1. The first term accounts for the scenario where passenger 1 selects their own seat, while the second term represents the recursive case where passenger 1 picks another seat, creating a subproblem with n1 passengers. This approach, implemented iteratively or with memoization, reduces the time complexity to O(n). While efficient, it still requires iterative computation for each n and doesn't leverage further simplifications. A deeper mathematical analysis leads us to the most elegant and efficient solution. Surprisingly, the probability that the last passenger sits in their correct seat converges to 0.5 for any n greater than 1. This constant pattern emerges naturally from the recursive formula. For example, for n equals 1, the probability is 1, as there's only one seat. When n equals 2, the probability becomes 0.5. For n equals 3 and beyond, the recursive structure stabilizes, resulting in a constant probability of 0.5. This insight eliminates the need for iterative computation entirely. We can directly return 0.5 for any case where n greater than 1, making this approach both time-efficient and mathematically elegant. The time complexity is O(1), as the solution requires only a simple conditional check. This derivation highlights how understanding the underlying structure of the problem can lead to significant simplifications. The chosen strategy for solving this problem is the direct mathematical derivation. This approach stands out due to its simplicity, optimal time complexity, and the deep insight it provides into the problem's structure. While the brute force and recursive approaches are valid, they involve unnecessary computational overhead. By recognizing that the probability stabilizes at 0.5 for all n greater than 1, we efficiently bypass iterative or factorial computations. This method not only achieves the best performance with an O(1) time complexity but also demonstrates the power of mathematical reasoning in problem solving. Combining efficiency with elegance, the direct derivation is the clear optimal choice for tackling this problem. In this problem, we are tasked with calculating the probability that the last passenger, passenger n, ends up sitting in their assigned seat under a specific set of rules. The first passenger picks a random seat, and each subsequent passenger either sits in their assigned seat if it is available or chooses randomly from the remaining seats. To approach this, we recognize that the problem has a recursive structure. For example, if the first passenger does not take their assigned seat, the scenario essentially reduces to a similar situation with one fewer passenger in seat. This recursive nature allows us to analyze how the probability evolves as the number of passengers increases. Additionally, there are critical base cases to consider. If there's only one passenger, they have no choice but to sit in their seat, so the probability is 1. For two passengers, the first passenger either takes their own seat or the second passenger's seat, each with equal probability, leading to a result of 0.5. Using this, a general formula can be derived: the probability for n passengers, p, n, equals 1 divided by n, which accounts for the first passenger taking their own seat, plus the probability of the recursive case scaled by the chance that the first passenger does not take their own seat. This formula becomes the basis for solving the problem mathematically. Here, the formula p, n, equals 1/n plus 1/n, asterisk p, n1, breaks down the probability into two parts. The first term, 1/n, represents the chance that the first passenger directly takes their assigned seat. The second term, 1/n, asterisk p, n1, captures the recursive scenario where the problem reduces to n1 passengers. Surprisingly, solving this recursively reveals a fascinating result. For all n greater than or equal to 2, the probability converges to 0.5. This simplification significantly reduces the complexity of the problem. Instead of performing recursive calculations for large values of n, we can leverage this insight to directly conclude that the probability is always 0.5 for n equals 2. To implement the solution, we begin by handling the base cases. If n equals 1, the result is 1 because there's only one seat. For n equals 2, we use the derived value of 0.5. For larger values of n, the recursive formula can be applied iteratively, but given the convergence to 0.5, we can optimize further by returning this constant value directly without performing additional calculations. This insight leads to a highly efficient implementation. The algorithm simply checks the input size and returns the appropriate result. If n equals 1, we return 1. Otherwise, we return 0.5, as derived earlier. The simplicity of this implementation means that no additional data structures are required, and the space usage is constant, or O1. Similarly, because the solution involves a single conditional check and no iterative or recursive calls, the time complexity is also O1. This makes the algorithm extremely efficient, even for very large values of n. The Python code provided reflects this simplicity. If the input n equals 1, it returns 1.0. For all other cases, it returns 0.5. This compact implementation is a direct result of identifying the steady-state behavior of the recursive formula and leveraging that insight to avoid unnecessary computation. With this understanding, let's consider edge cases and key takeaways. For the smallest input, n equals 1, the probability is clearly 1.0 since there's only one passenger in one seat. For any n greater than or equal to 2, the probability is always 0.5, regardless of how large n becomes. Even for extremely large inputs, such as n equal to a billion, the algorithm remains efficient because it immediately returns 0.5 without performing extra calculations. This problem highlights several important lessons. First, many complex problems can be simplified by identifying recursive patterns, but recognizing when these patterns converge to a steady-state result is equally crucial. Second, this problem demonstrates the power of deriving constant time solutions, which can handle even the largest inputs with ease. Finally, this solution underscores the importance of mathematical insight in algorithm design, as the key to this problem lies in understanding the recursive formula and its simplification to a constant result for large n. The solution to LeetCode problem number 1227, airplane seat assignment probability, can be derived using a mathematical observation rather than direct simulation. Let's go through the code step by step. First, we define the function nth person gets nth seat within the solution class. This function takes one parameter, n, representing the number of passengers and seats. The first if condition handles the base case where n is 1. If there is only one passenger, that passenger will always sit in their assigned seat because no one else is competing for it. Therefore, the probability in this case is 1.0. For all cases where n is greater than or equal to 2, the probability that the last passenger ends up in their assigned seat converges to 0.5. This result is derived through mathematical reasoning and recursive probability analysis. Instead of simulating the seating process, we use this direct formula to return 0.5 for all n equals 2. The function is concise and efficient, with a constant time complexity of O1, since it involves only a couple of conditional checks and returns a pre-computed value. By leveraging mathematical insights, we avoid the need for complex simulations or recursion, making this solution elegant and optimal for large values of n. Overall, this implementation is both simple and powerful, solving the problem in the most efficient way possible. This Java implementation mirrors the logic of the provided Python solution. It uses a conditional statement to determine the probability based on the value of n. If n is 1, the probability is 1.0, as the first passenger will always sit in their own seat. For all other cases, n equals 2, the probability is always 0.5. The implementation maintains clarity with concise code and adheres to Java conventions such as type declarations and a complete class structure. The problem we're tackling involves passengers boarding an airplane with exactly as many seats as there are people. The first person chooses a seat completely at random, while each subsequent passenger takes their assigned seat if it's available or picks another random seat if theirs is already occupied. Now, the key insight here is that when there's only one passenger, the outcome is straightforward. The person has no choice but to sit in their assigned seat, so the probability is 1.0. However, for two or more passengers, the problem reveals a fascinating symmetry. Regardless of how many passengers there are, the probability of the last person sitting in their assigned seat stabilizes at 0.5. Let's begin with the simplest case, where n equals 1. Here, since there's only one person and one seat, they must sit in their assigned seat, making the probability 1.0. The state tracking reflects this perfectly, with an input of n equals 1 and an output of 1.0. Now, consider the case where there are two passengers and two seats. The first person picks a seat at random, and there are two possible outcomes. If the first person picks their own seat, which occurs with a probability of 1/2, the second person will naturally sit in their assigned seat, resulting in a probability of 1.0 for this scenario. On the other hand, if the first person picks the second person's seat, again with a probability of 1/2, the second person is forced to sit in the first person's seat, which means the probability here is 0.0. Combining these two outcomes, the overall probability is calculated as 1/2 times 1.0 plus 1/2 times 0.0, which equals 0.5. This illustrates the symmetry in the problem, as reflected in the state tracking. With an input of n equals 2, the first person's seat choice is random between the two seats, and the combined probability is 0.5. Let's extend this to the case where there are 3 passengers and 3 seats. The first person again picks a seat at random, with an equal probability of 1/3 for each seat. If they pick their own seat, the problem reduces to the n equals 2 scenario for the remaining 2 passengers, and we know from the previous case that the probability is 0.5. If the first person picks another passenger's seat, say passenger 2's seat, the problem becomes recursive. Either passenger 2 or passenger 3 will eventually end up in their own seat, and due to the symmetry in seat assignments, the probability stabilizes at 0.5. This symmetry generalizes for any n greater than or equal to 2, where the recursive nature of the problem ensures that the probability remains 0.5. The state tracking confirms this. With an input of n equals 3, the first person's choice is random among 3 seats, and the recursive symmetry keeps the probability stabilized at 0.5. For the final implementation, the base case returns 1.0 for n equals 1, and for n greater than or equal to 2, the output is always 0.5. The time complexity of this solution is O(1), which means the execution time does not depend on the input size, n. The function simply evaluates the input and makes a decision based on its value. If n equals 1, it immediately returns 1.0, and if n is 2 or greater, it returns 0.5. Both of these involve a single comparison and a return statement, which are constant time operations. There are no loops, recursive calls, or any operations that scale with the size of n. This makes the time complexity constant, or O(1). Now, for space complexity, the solution is also O(1). The function does not use any additional data structures, such as arrays or hash maps, nor does it require recursive calls that would add to the stack memory. The only memory usage comes from the input n, which is a single integer, and the return value, which is a floating point number. These are fixed, constant amounts of memory, regardless of the size of n. Therefore, the space complexity remains constant, or O(1). Let's consider how this approach compares to a brute force or naive solution. A naive method would involve simulating every possible seating arrangement. First, you would generate all permutations of seat assignments, which has a time complexity of O(n). Then, you would check each arrangement to determine if the nth passenger gets their assigned seat, and finally compute the probability by dividing favorable outcomes by the total outcomes. This method is computationally expensive, with both time and space complexity growing rapidly as n increases. In contrast, the optimized solution leverages mathematical properties of the problem. For n equals 1, the probability is clearly 1.0, and for n equals 2, the probability simplifies to 0.5 due to the symmetry in seating outcomes. By avoiding simulation entirely, the optimized approach achieves O(1) time and O(1) space complexity, making it far more efficient. Finally, let's break this down into best, average, and worst case scenarios. In all cases, the time and space complexity remain constant at O(1). In the best case, when n equals 1, the function evaluates the condition and immediately returns 1.0. In the worst case, for n equals 2, the function evaluates the condition and returns 0.5. Even in the average case, the execution is unaffected by the size of n, as the computation is always constant. This consistency is backed by the mathematical properties of the problem. When n equals 2, the symmetry in seating arrangements guarantees that the probability of the nth person ending up in their assigned seat is always 0.5, regardless of n. This eliminates any need for computations that scale with input size, solidifying the efficiency of this solution with O(1) time and space complexity. Now, let's discuss some common mistakes that can occur when tackling this problem. First, a frequent misunderstanding is to assume that passengers only choose from unoccupied seats. This is not true. Each passenger can select any seat, including one that is already occupied, which creates the chain reaction fundamental to solving this problem. Another mistake is overcomplicating the solution by trying to simulate all possible seating arrangements. This leads to a factorial time complexity, which becomes computationally infeasible as the number of passengers, n, grows larger. For instance, at n equals 10,000, this approach is simply not practical. Then, there's the issue of forgetting base cases. Special cases like n equals 1 or n equals 2 are critical and need to be handled explicitly, as missing these can result in incorrect outcomes. Additionally, randomness in this problem is often misinterpreted. The randomness governs the seat selection process, not the probabilities directly, so it's important to distinguish between the two. Lastly, numerical precision errors can arise when working with probabilities in floating-point arithmetic. To avoid these, minimize unnecessary computations that could introduce rounding issues and ensure your calculations remain precise. This problem is often used in interviews to test probabilistic reasoning and pattern recognition. Instead of brute forcing, focus on recognizing patterns, as that's the heart of solving this problem. One key insight is that for n greater than 1, the probability of the last passenger ending up in their assigned seat is always 50%. This result stems from recursive reasoning and symmetry, which you'll want to explain clearly during an interview. Being able to articulate why the probability stabilizes at 50% is crucial, as it demonstrates a deep understanding of the problem. Interviewers are likely to ask about this, so be ready to walk through the recursive logic step by step. Avoid simply stating the answer is 50% without justification, as this can make it seem like you've memorized the solution without truly grasping the reasoning. If you're looking for related problems to practice, consider LeetCode number 935, Night Dialer, or LeetCode number 688, Night Probability in Chessboard. Both involve probabilistic transitions and recursion. Additionally, while LeetCode number 121, Best Time to Buy and Sell Stock, isn't directly related, it tests similar skills in recognizing patterns and making optimal decisions. For a more challenging problem with recursive reasoning, you can check out LeetCode number 1770, Maximum Score from Performing Multiplication Operations. There are alternative approaches to solving this problem, each with its own trade-offs. One option is a simulation-based approach, where you simulate the seating process multiple times and calculate the empirical probability from the results. While this method is intuitive and straightforward to implement, it becomes computationally expensive. Exact simulations have factorial complexity, and even empirical trials require O(k*n) time, making this impractical for large values of n. Another, more efficient method is to use mathematical derivation. By leveraging recursion and symmetry, you can directly derive the 50% probability. This approach is optimal, as it has O(1) complexity, but it does require a deeper understanding of probabilistic reasoning. Finally, a dynamic programming approach can be used, where you define a DP table to represent the probability of each passenger getting their assigned seat. While this method is correct, it's often considered overkill because the problem can be solved much more simply using the mathematical insight. As a result, DP adds unnecessary complexity and is not recommended for this specific problem. Great job following along. We've summarized the key points of this problem, leveraging mathematical intuition and probability to arrive at an elegant solution. This problem highlights the importance of spotting patterns and simplifying complex scenarios. Thanks for watching, and don't forget to like, share, and subscribe for more content like this. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!